So good afternoon to everybody, and welcome back to today's session. So today I'm pleased to introduce our next speaker, who is Professor Nicola Bellomo. So Professor Bellomo has developed most of his career at the Polytechnic University of Torino, and he's now distinguished professor at the University of Granada, and also researcher at the Institute for Applied Mathematics and Information Technologies in Pavia. He's a recognized specialist in the field of mathematical modeling, analysis, and simulation of PDEs arising from natural and social science. And more specifically, he is expert in living complex systems and pioneer on the development of kinetic theory of active particles. He has also led several European projects on crowd dynamics and social conflicts, together with the interaction between mathematics and ecology. So Professor Bellomo is editor-in-chief of the journal Mathematical Models and Methods in Applied Science, and he's also ranked as a highly cited mathematician in Web of Science in the last years. So today he's going to talk about modeling of various pandemics in global connected world, a multi-scale system, a multi-scale active particles approach. So please, Nicola.
Okay, thank you for the presentation. Thanks also to the organizing board of the University of Granada, who has devoted some time to organize this web BIOMAT, which is, however, reaching a huge number of persons because we need communicating. And I will be talking about a problem which is affecting our daily life, our safety, our economy, and everything. So it is about the modeling of pandemics in a globally connected world. Indeed, the problem cannot be localized, but is affected all over the world. And it is a multi-scale problem. So the presentation is in three parts. The first part attempts to explain the main concept of the complexity of this very, very special system. And then I will, out of this first preliminary analysis, I'll move to modeling contagion and in-host dynamics, and then about some simulation and research perspectives. This talk is also dedicated to Albert Camus. He was my favorite author when I was in high school many years ago. I don't say how many because it's a lot. And then it is important that in his book La Peste, human behaviors became say less selfish to overcome the problem of the peste noire, and now we have the same problem in our society. It is a world problem because the pandemics has spread everywhere, and communications is one of the ways by which pandemics is transferred from one person to the other. Well, the support to this talk is a paper which is an interdisciplinary paper where some applied mathematicians have linked their destiny to that of virologists, two virologists, one immunologist, and two economists. Also, we have been involved in a project, a voluntary project promoted by the Royal Society, a call for assistance to the scientific modeling community. Our task was the INOST modeling, and it has been an important way to communicate at an interdisciplinary level. I also bring to your attention this website, which is daily updated, as well as the lectures which have given open source, are given open source by the University of Granada in the modeling nature site. And these lectures gives the real mathematical background of this talk. It is mainly for young researchers in a situation where they cannot easily travel and have the vis-a-vis communication, which is very important also in science. So about the virus, there would be a lot of things to say. And when it started, not everything was known, and even virologists were surprised. But I just want to mention a few things. One is that the virus is generated by a mutation. And the mutation keeps going on because this virus has an ability to mutate, which highly surprising. It is not a black swan. I will go back to the black swan concept again, but it was not really a black swan. Someone had given alarm. Even Bill Gates gave an alarm about the danger of viruses. But what is true is that our society was not ready to tackle the problem. And the beginning has been very hard. It also, I would like to mention this is personal idea, I don't want to impose them to everyone, but I wish to mention that in my opinion, this kind of problem cannot be tackled by a standalone approach. Mathematicians have to communicate with the expert in the field. I mean, virologists, immunologists, biologists, and clinicians, and so on. And it not only mathematics with biology and medicine. The problem also involves economy and sociology, because the way by which these virus and the pandemics affects our life is also going over huge problems of economy and social situation. But we have to trust the idea that mathematical models, once validated in some sense, then can provide a useful information to the crisis managers. So mathematicians have a role, have an important role, but they should invent something new. They cannot be a technical manipulation of the deterministic population dynamics, and we have to tackle multi-scale problems because we have several scales constantly interacting. The one at the molecular scale at the level of genes, whereby a virus which mutates continuously. And in the lung, we have a competition at the level of virus particles and immune system particles, but affecting individuals, namely at a higher scale. So we have to invent something, as the Nobel laureate Lee Hartwell taught us 20 years ago. And so I also wish to mention that I personally don't like the term soft science. The science is that of living systems, as also in the website of Granada University. So the strategy, rapidly the strategy we follow to reach the target of mathematical equations, namely mathematical models. The phenomenological interpretation of reality should generate an interpretation of the complexity of the systems, the complexity features. The complexity features should be captured by a mathematical structure, which replaces the field theories which are not available for living systems. So far, then if we are capable to interact in modeling interaction dynamics at all scales and interactions across scales, as well as external actions, then we replace these models, sub-models, in mathematical structures and obtain derivation of models. Model validation, and then we can open a dialogue with crisis managers at all levels, at the level of medicine, but also at the level of politics. Of course, there are mathematical topics and simulation problems, highly tricky and challenging, but I will not talk about this this time, maybe in another time. For the moment, we are strongly engaged in the modeling issues. So let's recall that the five, for my opinion, most important features of complexity, which should be captured in the modeling approach, they go from the ability to express a strategy, thanks to also to Lee Hartwell, up to Darwinian mutations and selections, which is affecting our fight against the virus. Let us rest a little bit. Let us look at this beautiful Esker representation of a small village. I claim, but I leave it to you about the investigation, that this representation is somehow captures some aspect, the five aspects of complexity I was mentioning before, including the black swan. The black swan is the passage from the peaceful village to the chest of plate. This is an important picture for me also because, as someone knows, I was born in this house many, many years ago. So given a strategy, we move towards equations, and I want to mention right from the beginning that the model cannot simply give the number of infected people. And it is much more important, the information which must be much more rich. We have to give information about the need of hospitalization, the progression of the illness, as well as on the people who unfortunately risk to die or die. So this flow chart gives you a first idea, which is the idea of the model which I'm going to present. We have individuals, they get infected by social contacts, but also short and long range interactions appear because short range means contact during the dynamics, but long range involves transportation dynamics. And healthy people become infected, and then the in-host dynamics, it's at a different scale. It's the competition between the immune system and the virus proliferating. Actually, and then what happens? People can recover, may need hospitalization with therapeutical actions, and even die. So it's a vision which goes far beyond the vision of SIR models or modified SIR models. And now applied mathematician, I've seen several one, also someone listening this talk, like Lorenzo Pareschi, who have understood this, this message and are working in this direction. So I have illustrated and I can move to the contagion problem. The contagion problem is in a population, a number of individuals where and a small number of them, maybe even very, very, very small, maybe just one, is initially infected. The frequency of contacts is the origin of infection, but it is not the only origin of the infection. It is the problem. It becomes straight away multi-scale, because also the level of the infection is dangerous. The stronger is the proliferation, the number of viruses in the lung becomes higher, and their rejection becomes very, very dangerous and very effective. So contagion is already a multi-scale problem. So we have to take then subpopulations which play the game, which are called in the kinetic theory for active particles, are called functional subsystems, but also we have to identify a progression both of the virus, which progresses towards the higher states, and the immune system, which gradually and luckily learn, moving from the innate immunity and to the active immunity, which has also some memory. So if we have represent the functional subsystems by a probability distribution over the microscopic state, in this case, discrete is more reasonable because the continuous distribution is not, cannot be really tuned by experiment. And so we have four populations which are the healthy, infected, recovered, and die. But inside each population, we have different stages which determine the need of hospitalization and the recovery, when the immune system and therapeutical action as well are capable to bring the defense against the virus up to the depletion, the destruction of the virus. The mathematical structures which belongs to the mathematical theory of active particles is this one. Well, a role is played by the encounter rate, which depends on the position mainly, but also on other quantity, and the transition probability, which show due to interactions individual entity change their microstate and macrostate at the same time. This is just a structure. We model interactions, which is a competition, as I mentioned before, and I localize the dynamics in the easiest case, namely this flow chart, where alpha represent is a sort of mechanical parameter. It is the level of confinement. Which depends on the distance between person, the fact that they put a mask, and so on, and other devices. And then despite a level of confinement, then they may even become infected. And the competition is ruled simply by two parameters in this very simple model. One is the progression ability of the virus, which is beta, and gamma is the defense ability of the immune system, which can make the progression ability of the virus regress. Actually, this beta parameter is subject to the what we call mutations, and also on the newspaper is the name variance is used. Variance means that the mutation is favorable to the virus, because if it is not favorable, then the virus loses. That virus in that lung loses. While another one, if actually mutations are simply error in the reproduction, error in the DNA, in the reproductions, and so the virus can have a negative for him, positive for us, mutation, or a positive for the virus, but negative for humans. So going on, actually the model takes the following form, is the following structure. Here I've not put transportation term. This is the next step which we want to develop, but we have to think about. It's not so rapid, so immediate. So we have a tool now. We have a tool which shows interactions and probability of transitions, which has been now formalized, and we can investigate the predictive ability of the model, and what it can, the information what it can give us. This is a very important topic because it looks at future activity. The problem is very far for being closed. We are at a very initial state. What I'm going to present is only the very preliminary state. Well, it has been for us a huge effort, but we are already working on a more ambitious program. I will mention at the very end. So we have a model, and we investigate something which is affecting our life, the locking and the downlock dynamics, which is the only way we can nowadays control the pandemics. Of course, we can do it by vaccination, but also the problem, vaccination is not really, not yet active. So what do we know? The information which is available. Well, this is the mortality rate in all countries, but is not, unfortunately, is not reliable. This figure is not reliable. I've been talking with serious and strong epidemiologists, and they say that only the qualitative behavior is true, but it became reliable since December last year. So now we have data on which we can make the tuning. The tuning on this data cannot be done. But what is really different that in all countries we have a growth of died people and then an asymptotic value because the problem has been controlled, but this is not true now because after the second wave, they started to grow, but in some countries like United States, the rate of growth has been almost linearly growing all time. But if we look at a wave, we can observe a first wave, the onset of a second one in different, with different time in different countries. Sweden was the first to have the second wave due to the lack of downlock. In the United States, well, we have seen many things about United States, even the attack to the Pantheon, but European countries have a somehow similar problem because the second wave was generated by summertime and lack of locking, lack of being careful, and then we are now facing the problem of a possible third wave. The problem is that the second wave can be much worse than the first one, as we shall see soon. So we want to understand what is the meaning of the first locking, first delocking, downlocking, and then the onset of second and further waves. It is very important to understand these kind of things because I'm afraid that on the newspaper which we read every day, this concept is very far from being clarified, and even luckily not all crisis managers are not fully aware of that. So we can play with two parameters in this very simple problem. Of course, when we may study the more complex, it is going to be higher the number of parameters. But what play the game is the ratio between the proliferative ability of the virus and the immune defense ability, and the parameter which multiplies this data, which belongs to the individual, to the level of confinement, namely by alpha, which is not a parameter, constant parameter. It depends on time, depends also on the action of crisis managers. So what can we study? Okay, we can study the number of infected population in the first wave. The first wave, there is a growth and then a decay. And it is important to also to compute in the red line is the people who need anyway hospitalization. And this should be compared with the level of hospitalization, because this red line can pass this. This is exactly what it happened in Italy, in the region of Bergamo, at the very beginning, and which was treated by the Chinese people of Wuhan by building up an hospital, not for everything, an hospital only specialized for this kind of illness, and so they have not influenced the normal hospitals, which are also important for people who have other disease. On the French journal today, yesterday already, Le Monde was reporting about the situation in Marseille, where it seems that there is no, the number of hospitalized is so high that other illness are put in on a second stage, and this is also very dangerous. So in the the model can explain the asymptotic behavior of person who recover, person who need hospitalization, and those who ultimately die anyway. In fact, this is one of the cases where the number of recovered person, the person who need hospitalization is higher than the level of the hospital to receive persons with this kind of pathology. But we have also to understand that before just T1, there is the onset of the pandemic. Then, luckily, a locking is imposed. The locking is imposed, there is a growth, but also a decay. And this is not simply experiment. This is the mathematical model which has the ability to explain everything, all what is in this figure. So what can we do? People say, we want to go out, we want to have a normal life, so let's stop with this locking. Okay, if we stop the locking too early, it's even worse, because it goes up and can be much worse than the peak of the locking. But if we wait, we can have a lower wave. Anyway, we have a wave, but we can also move towards a silent state, low-level silent state. It is not zero, like the SIR models explain. It is small, but is higher than zero, and then this means extremely dangerous. So we say, okay, we fix a reasonable locking time, but the delocking level, if it is full freedom, as it happens in many places in Italy, but also in other places of Europe, then we can have a wave which is much worse than the previous state. If it low it, they make it better than the dark one, the black one, but sufficiently low, then we have the wave. But if we control it with some graduation, say, let's make it think that alpha can become a sort of function of time, then we go to the silent state. But it is not an equilibrium, it is a meta-equilibrium. Small perturbation generate a second wave. The second wave, it depends. If after the silent metastability situation, the delocking is reasonable, then we have a second wave, which is smaller than the first one, which, however, creates dead people. dead people anyway, and the recovered one, they are also the infection level depends on the level of the locking. So if we make even in a delocking situation, if there is a not sufficient control, we are very far from the very beginning where no one was caring. Here we care, but we don't care enough. And if we don't care enough, we have a second wave, which is much worse than the first one. So it is extremely important having a continuous control of the situation, and crisis managers should say almost day by day how individuals should behave. So we can have a third wave also in the case of a small second wave. I have not put in the simulation the very bad case because I want to be a little optimistic about that. So what can we do? What can we do? This is my idea how the approach should be developed. We should include vaccine and mutations. The two things merge together. And we have to include heterogeneous population, where heterogeneity is not so easy to classify because it is roughly related to age, but it's not just age. There are a lot of other sources of heterogeneity which play the game, and the action of vaccines generates an immunity which is not for life. We must know that. Network dynamics which bring individuals from one region to the other and generates new infected people or take away infected people. Then we go to the in-host dynamics, where the mechanics of the lung should be taken into account, and then the usual story, recovered, hospitalized, dead. At my age, I cannot be so naive to think that if a couple of mathematicians can play this game by standing alone. I think that this is an idea of an international cooperation, or at least national cooperation, because the problem is too complex, and it is not a problem that we can move step by step with small steps, modify the SIR model and so on. It is a tricky problem which deserves attention by several people, and in a interdisciplinary project. So this is my rev. I don't know, I will do it, but I at least I hope that the young generation collaborating will do it. So to give an idea, when the result may have been appeared to you little oversimplified. We have new ones which already account about something of the previous slides, but a lot of serious mathematicians and scientists in general have been collaborating from different field of expertise, as I said before, mathematicians, but also a person with some familiarity with computer sciences and computing, like Livio Gibelli in Edinburgh, and virologist Bingham and Tuarok, and immunologist Guido Forni. I've learned a lot from him about the immune competition, and then some experts in economy, Giovanni Dosi, Pietro Terni, and Marica Virgilito. So I have to thank to all these co-authors and co-lecturers of the lectures I mentioned before, and I wish to thank the organizer once more, but also the audience and all the suggestions they will give towards a modeling approach which can predict what is not predictable. This is the philosophy of Nassim Taleb about the black swan. So, thank you. So,
Thank you, Nicola.
Do I stop sharing the screen?
No, I think you can keep it just in case it helps for the question round.
Okay, okay.
So as we said before, if you want to pose questions, please at least write down something in the chat, and then we will give you the turn to do it, to ask directly to Nicola. Well, while the people is warming up, I would like to pose a question myself, Nicola. So could you tell us a bit how has been the interaction with the authorities so far, broadly speaking, in terms of getting more data to feed your model, for instance, or in terms of posing your proposals to some crisis managers, that two-way route?
Well, collecting data has been for me easier, because there is in Italy a society of highly sighted, and in this society there are persons who get this information and find a way to epidemiologists and who can get this kind of information. And so we could get the data. We could get in some way get the data. An additional contribution was given by the RAMP project of the Royal Society. But what is very important now is collecting the very recent data, because at the beginning there was a manipulation of all data, and none of them could be defined fully reliable. Well, a problem with crisis managers. Well, as I said, here there is a little of politics. I'm sorry. The crisis, when the crisis manager were not even existing before the pandemic, while a nation should have them. And politics has been always reluctant to scientists. Someone even thinks that the science is a sort of hobby of some intellectuals who play with, in our case, with mathematics and so on. Now, politics has understood that science is important, and that now the dialogue is beginning. But again, it is not a matter of a standing alone approach. If I go to a politician to discuss, well, I have to wait weeks before being able to talk. Actually, I have been able to talk, but not yet useful. What is very important is, I repeat what I said before, an international team who collaborate. Say, the Royal Society said, well, this is a startup. Now it is up to you to organize. And now it's up to us to organize a cooperation, and without thinking that the end of the story is an early end, we say within this year. It's going to last long for much time, and we have to learn to take all this pandemic, and so it's up to us scientists finding a good self-organization, produce result, and then attack with our results the crisis manager.
Thank you, Nicola. There are some questions in the chat, so we can start. Maybe first one is David Margepstein. That is asking, which is the difference between your model and typical SIR models?
Well, it's an enormous difference. The model includes heterogeneity, interactions at all scales, and probability, some stochasticity. But it cannot be compared in a few words, but is what the real answer is given in the first lecture of the open source lectures, which are available at the Granada website. And there is also a philosophy and a history behind these differences, starting from a long time ago, Immanuel Kant and the Schrödinger ideas have taught us a lot of things. And in the first lesson, this all is explained. But are not two things comparable, are two very different things. When I look at a good-looking lady, if I see two ladies, I can make a comparison, but I cannot compare a human with something else, completely different.
Okay, so we also have some question by Thomas Hillen, but I think we can activate his audio.
Yeah, now it's
okay. Yeah. So Nino, thank you very much for a nice talk. It was very inspiring. I wanted to ask your opinion. And so many people in Corona data use machine learning, and they would say machine learning can make much better predictions than mathematics can. So do you see this as a competition to math, or would you say we should all do machine learning now? What's your opinion on that?
Well, this is very key question, which really deserve attention, because machine learning, with my opinion, say, I cannot force everyone, but machine learning without a filter cannot learn. We need a mathematical model to filter. Then, if we have a good mathematical model, I don't say mine is the good one, I say a good mathematical model, then we can use machine learning to work out the crisis managing. This is exactly what we did in the European project on crowd dynamics. We had a model of crowds, and out of that we could figure out several dynamics, and then filter them with data comparing by some concept of convex distance, what is reality, what is predicting the model, and the model includes the crisis managing. So these two they are distant relation. Mathematicians and the people who work in artificial intelligence, they should talk more and teach each other how to tackle the problem. I don't believe that machine learning without a good a good model filtering reality can effectively learn. And I don't think that a good model, if it's not put in a machine learning dynamics, can effectively be helpful.
Okay,
Very
thank you.
important
Thank you,
question. Thank you.
Okay, next we have Francesco Cavalleri. Would you like to turn your microphone on and formulate your question?
Yes, thank you. And thank you for the talk. I want to ask, in your opinion, what is the most reliable data and what you have used to tune the models? Because, for example, the saturation of hospitalized is not clear if it's a real saturation or is the saturation of the hospital system or the fraction of positive PRC depends on the policies. What you use to tune the model?
Well, unfortunately to say, the most reliable data is the number of dead people. This is a reality which is now has been carefully filtered, and it is reliable only by beginning of December. So the other data, some of them are reliable. Say the level a hospital can accept is also reliable, but depends is a local information, is not a universal information. So the tuning, first of all, we have to investigate the different scenarios of the model can offer, and the scenarios must be rich, not simply limited to infected, and then do the tuning not just by mathematician. We have to do the tuning with the people in a certain region and with a certain information we can discuss with them. That's why I was talking about a cooperative effort.
Thank you.
All right, so next we have a question by JC. At least this is the acronym that shows up in the application, and the question is related with the kind of data you can use to feed your model. So JC, would you like to formulate the question yourself? Else I would read it out.
Hi, good afternoon. Well, I think my question is well answered with the question just before. So thank you for your talk, and that's all. Thank you.
Okay, thank you to you for the question.
All right, so far we don't have any more questions in the chat. So if you would like to pose any other issues to Nicola, you have another chance. Yes, we have Elena Torres who would like to ask something. So if you will, you can start your microphone and formulate it yourself.
Yes, thank you very much for the talk, Nicola. And I would like to ask about the parameters used in the model. I think the parameters are used to introduce some aspect of reality in the model. And I want to know how you choose the value of the parameter so it represents reality correctly.
Well, there is a procedure, a mathematical procedure. So first of all, we have to put the model in a dimensionless setting, so that all variables belong to the domain 0, 1. This is very important. It's also a computational check. When we do the computing, we, for instance, have to check that the number of the sum of all population goes to 1. This is a trivial check, but it's very, very important. Then if we do this the dimensionless setting, also the parameters get and exist a reasonable physical domain. Out of that, once we have made this setting, the second operation is experimental. I mean, computing. We must do what is called the scenarios due to the different values of all parameters. So we must have a number of parameters which is small and possibly or necessarily related to the type of phenomena we take into account. So the parameter is not an anonymous parameter. It is a parameter which has a name: immune competition, proliferation, confinement, and so on. And so when we have all the scenarios, we understand which parameters are important in the dynamics, because some of them may not be relevant. This is not the case of these physical systems, where the minimal model with the limited number of parameters is absolutely necessary. We cannot hope that some of them are not significant. So once we have these scenarios, then we may say, now I want to make the model validate for the application. Well, it is validated in two ways. First of all, it has, since the system is complex, it has to reproduce all emerging behavior. And sometimes the model is even capable of showing new behavior, new emerging behaviors we were not before observed. We had this experience in the case of the immune competition. But in this case, the emerging behaviors have been observed. And now we say, now I want to have a model not only validated, but also specific for the application. So I need additional data. And these additional data are very heterogeneous everywhere. So I have to localize them. And I can, if a real situation, a region can give me this data, it's not a huge problem giving values to the parameters, but these are valid to that specific case, not for everywhere, because the system is all over the world and is extremely heterogeneous. Now, I stop here because this is a very important problem and should deserve a very, very serious serious investigation and research activity, because it is not simply a technical problem. Thank you for the question.
Okay, if you want, we finish with a couple of additional questions. One of those would be by Nofelhatin, if I pronounce it properly. So if you want to activate your microphone.
Do you hear me?
Yes, I do.
Thank you. First of all, thank you, Professor Bellomo, for the talk, and thank you also for the BIOMAT 2021 organizer. In reality, Professor, we cannot trust data because for example, if we have an infected person at T1, but we will identify him as an infected at T1 plus another time at T2, for example. For the authorities, they will identify him as an infected infected person at T2. So we cannot trust data also for dead people, because PCR tests are very expensive. So for poor countries, for example, they will use PCR tests for living people, not to verify if a dead person is die due to coronavirus. So mathematical model for COVID-19 will just have an overview how the COVID-19 spread and the effect of any intervention. We cannot talk about fitting data with the model. Is my opinion is true, or I didn't see things correctly?
Well, it's true, but it should be seen in a broader vision. We have a world pandemic, which is a world problem. If we think that rich country the countries who can buy the vaccine and vaccinate the population are safe and can be safe and happy. No, I don't say with their inside the cautions, but someone think that if I have the money, I have solved the problem. No, it's not like that, because this is a mutating virus. So if we leave out poor countries, the virus will mutate there and will reach the rich country very, very shortly. So it is a real world problem which has to be thought in a richer and broader vision and more altruistic vision, as in the La Peste of Albert Camus, which I presented in one of my first slides.
All right. Let's proceed to the final question by David Mark Epstein. Would you like to formulate it yourself? Okay, if not, I can read it out. It's about the basic reproduction number. Is the basic reproduction number a parameter in the model?
Yes, I mean, it's not that one. It's something which has to be computed out of detailed calculation, and depends. Is not so simple computing the reproduction number, because it depends on the model, and I cannot apply the Sierra theory to this model. So I can compute the the speed of infection and related to the overall population, but is a totally different calculation.
Okay.
A last question for my part. You mentioned that you are interested in add some transport terms in the model. Then you refer to transport in what kind of variables in space, in activity. Is important the transport in space or in activity? How you do think? What is your feeling about?
Well, in this case, it is very, very, very important the transport in space. And in the activity, it can be included in therapeutic actions. It's more important than the inner transport in the activity. In the space, there are two types of transportation, three types of transport terms. First, I want to understand what happens in a crowd, in the population of the Movida, what they do. There are people, Annalisa Quaini, Houston University in Texas. She's working on this topic, and I've discovered that also the team in Kaiserslautern is working. This is one of the aspects of the space dynamics. Another aspect is propagation somehow continues in the territory. In this case, rather than, in my opinion, rather than looking at linearity and non-linearity of the diffusion term and also transportation, diffusion and transportation can be linked together in some sense. The problem is the heterogeneity of the territory with preferred propagation line, but not unique. Is not one line or two lines. Is a far more complex problem. And transportation in networks. Transportation in networks means that you have a dynamics of migration from one network to one node to another one, and the people who move around are carriers of a pathology. So this is a very, very tricky problem which deserves a careful modeling. Mathematician likes very much proving theorems. I am too old to prove theorems, but now it is time to produce good, reliable models. And then a huge amount of possible theorems will appear in the sum. But without good models, we may have useless theorems. First the model and then the theorem.
Okay, thank you.
Thank you.
Well, if there is not more question, then we would like to thanks again Nicola to give this nice talk, and we wish the best for this COVID recovering for all the people.
Okay, thank you to you. Thank you to the organizer, Juan and David, and thank you to the audience also for the questions which have been posed. Thank you.
Thank you very much.
Thank you very much.
Let us remind you that next week we will have a seminar by Alexander Mohilner, who will speak about the mathematics of mitotic spindle. We'll send you the links probably next Tuesday. Thank you, everybody.
Thank you.